In this video, I would like to demonstrate the solutions to exercises 1 and 2 from the notebook Multivariate Linear Regression. In the first exercise, we will fit multivariate linear regression model using normal equation. And we will do it by first splitting the dataset into training and test set, where we will include the first 120 samples in the training set. Then we will implement fitting of the model using the normal equation. We will predict the target values according to the model. And finally, we calculate the root mean square error according to this equation. So here is the list of useful functions that we will need. So it's hstack for concatenating two Numpy arrays, matmul to perform matrix multiplication, matrix.t to transpose the matrix, and mp linalg inf to invert the matrix. Okay, so we will start by creating the feature matrix with the extra feature x0 that is equal to 1. So we need to add a column of ones to our feature matrix X. And first we create this column, the code is already here, and then we need to concatenate this column with the feature matrix. And for that, we can use the function mp-hstack. So here in the argument, we say what we want to concatenate. So first the column of ones, and then the feature matrix. And here are some commands to print out the result so that we're sure we've done it correctly. So first we will print the first three lines of the new feature matrix, and then we will print the new number of features. And you can see here the column of ones and number of features increased from 6 to 7 because this is the data set with 6 brain tissues. Okay, now next step is to split it into training and test set. So we already have here equation for a training set. So we take the first 120 samples and we keep all the features. Next, we need to select the training target values. So there will be just first 120, and this is a one-dimensional vector, so don't need a second argument. And for test, we get the rest of the samples, so it will be x1, and we start at 120 and go to the end. And we keep all the features. And here we have already code for the target values in test set. And you see we have 120 samples in training set and 44 in test set. Okay, now this is the most difficult bit. We need to calculate the weight vector with this equation here. So first we can calculate x transposed x. So remember that our feature matrix that we are using is now called x1 train because we added the column 1 and then we selected first 120 samples for the training set. So we therefore have to multiply x1 train transpose, so dot t gives transpose, and with itself, so x1 train, this one not transpose. Okay, so that's the first step. So second step is to implement this bit of the equation x transposed y. So the beginning will be the same as the line above, matmul x1 train transposed, and this time it's times y. Okay, now we need to invert this xtx, mp linalg inv. There we go. And finally, we calculate the coefficient vector. So this first part is in this, and second part is in this. So it's np.matMove, and it's this variable first, and xty second. And let's see whether it worked. Oh yeah, y train. Okay, we should have taken only the training set. And that's it. Now it worked. So we see that we've got coefficients here, and it's how many we have? 1, 2, 3, 4, 5, 6, 7, which is good because we have 7 features in the new matrix. It was 6 plus that's the bias. So it seems all working fine. And now we need to predict. So equation for prediction is a feature matrix times the weight vector. But now let's be careful because that's predict on test set. So you actually need to use feature matrix of the test set that we called X1 test. Okay, and it's matrix multiplication. And second argument will be our weight vector W. Okay, hopefully this should now work. There is some code here for plotting. And that's our result. So in this plot, we have target values, the prescribed ones on the x-axis, and predicted on the y-axis. So if everything was perfect, they would be on the line y equals y predicted. Okay, so we see that most of them are nicely on the line. We seem to have some deviation here at the early gestational ages. So perhaps this behavior is in reality nonlinear. So we actually see there is a little bit of a bias here. So we will address that later on. But for now, we can say that the fit seems reasonable. So let's confirm that numerically by calculating root mean square error. So first we calculate the error between prescribed values on the test set, so y test, minus predicted. So that's y pred test. Just double check, that's what I called it, yes. So now next thing we need to do, we need to square this error vector, and that can be done by error 2 stars to the power of 2, and there is already the code to calculate the mean and then take a square root. So let's see what we get, and we got 1.78 weeks on the test set. So next I will demonstrate the solution to exercise 2. So in this exercise, we wanted to compare the performance of linear regression models with different numbers of features. So we had 3 different datasets. The first one contained only 1 feature, whole brain volume. Second one, 6 features, which were brain tissues. And the last one, 86 features, which were brain structures. Okay, so here I already have the code to load these 3 datasets. And I created here 3 different feature matrices, x1, x6, and x86. Target vectors are all the same. And here we're just checking that the number of features is what we think it should be, and everything looks fine. So now we need to calculate root mean square error on the whole set after fitting linear regression model. And if you did the activities, then you know that we created a function for that we can reuse. This function is here. It's called root mean square error. and it takes the model, feature matrix, and target vector. And we can very easily simply put all different feature matrices in, and with these functions we can very quickly calculate these values. So root mean square error, model x1, y, so that's for one feature. For 6 features, it's x6. And for 86 features, x86, y. Okay, let's run. Goes too fast. There we go. So you see that what happens is that root mean square error is decreasing with increasing number of features. But how should we interpret that? Is the model really improving, or it might be as well that we are overfitting? So to check that, we have to calculate root mean square error using cross-validation. Okay, so let's do that. We created a function for that as well during activities. It's called root mean square error CV, and it has the same type of parameters, so we'll be able to quickly solve this as well. So root mean square error cross-validation, now model x1, y. For 6 features, x6, 86 features, y. Okay, hopefully that will work. And a typo here. There we go. Okay, so now this is interesting. One feature, 1.6 weeks. 6 features, 1.27 weeks. 86 features, 2.08 weeks. So you see that from 1 to 6 we improved the performance, but from 6 to 86 the performance decreased. So the best model is 6 feature model, and we badly overfitted the 86 features with 86 features.